just before we look at that, the calculator, or the calculators, because there's one for pi type, one for T type, okay, available at that address, mandy.com. We're going to look at that in a minute. Right, I'm going to do the T type one just to show you how it works. Leave you to either, if we've got time today, go on the computers and do, or between now and next week, just check that the pi values come out the same, okay, with the pi type calculator there, and then that's good practice for you, okay. They require you to input the attenuation level in power dB, so that's the formula you need to calculate it. We substitute in for P out and P in. The formula, power is V squared over Z. Yeah. So we got the numbers we put in there as 10 log brackets 10 squared over 500, all divided by 20 squared over 500. And the result we get is minus 6.02 dB. And for the calculator, we need to strip off the negative value. All the minus sign is saying is that's a negative gain. So if we want it as an attenuation, we just take a negative sign away. If you put minus 6 in the calculator, it won't work properly. Okay? Because you're trying to build an amplifier. Minus attenuation is gain. Just like negative deceleration as acceleration, or deceleration as negative acceleration. You get my meaning? They're opposites of each other. Okay? So that's the value we need, okay, to be able to use the calculator. So if I go to chamandy.com, in good old Blue Peter fashion, I've already got this prepared. There are a number of calculators for various different things. These two are ones if you want to design an asymmetrical attenuator, different input and output impedances. You can use them to design a symmetrical one, but that will give you separate values for Z1 and Z3. They'll both be the same, but that'll tell you that there are two discrete values because it thinks you're designing, and that's going to ask for both an input and an output impedance, and you're going to enter the same values. So it will still work, but it's more complicated than you need. What you're looking for is either the pi attenuator, or, as we're now going to use, the T attenuator. T attenuator calculator. It now wants to know what the characteristic or system impedance is. Ours is 500 ohms. It wants to know what the required attenuation is, 6.02 dB. If we then click on calculate, it tells us what the ideal values of the series resistors and the shunt resistor are. 166.65 and 666.7 ohms. Yep. From that, we can have a look, and up here, it's quite handy, somewhere here, there's a link to preferred resistor values from different ranges. So what I usually do is click that with a wheel, so I get that open in another window, and don't have to keep flicking backwards and forwards. We've got various values from various ranges. E12 range of 10%, E24 range of 5%. Now, at the college, Chris buys 5% resistors, plus or minus 5%, but he only buys every other one in the range to keep the... We don't need to have every value, his view, we don't need every value in the 5% range, but largely they're the budget worst resistors available, if you like. Not many people bother with 10% these days. So he gets the values that are in the 10% range, but he buys 5% value resistors. What this means is that 100 in there means I can get a 1 ohm resistor, I can get a 10 ohm resistor, I can get 100, 1000, any multiple or divisor of 10 of that value. I can also buy in that range a 120 ohm resistor, 150. The idea is that the tolerances either side of those preferred values make up the difference between them, so that the tolerances make the values effectively overlap each other. In the 5% range, as you can see, I can get 110 in between, or a 1.1, or an 11, or 1100. So what we're looking for in our design, for our series resistors, we're looking for 166. If we go in the 10% range, we're going to either have to choose 150 or 180. Alright? For your lab, you don't really want to get it spot on. You don't want to make too much effort to get it spot on, because that'll not give you any difference between design and simulated performance. No, you don't want to artificially take it away, Luke. We're looking at what you would get in reality if you just picked preferred values out of a box. If they're miles away, then we might look at putting something in series or parallel to make it a little bit closer. But if you do too much of that, you'll have nothing, you'll have no difference to talk about in your assignment. That's not the idea of it. Okay? So we're looking at using 150 or 180 if we pick from the 10% range. So we'll go back in and we'll change that one to 150. We're also looking for something 666. Well, we've got a 680. The closest below that is 560, so we're going to choose the 680, aren't we? Yeah. Not always obvious. Sometimes it's worth going back and trying the other side after you've seen how much difference that make to your attenuation value, because you might prefer your attenuation being a bit bigger than design, or you might prefer it being a little smaller. If that's absolutely imperative that you don't overdrive that load, you'd want your attenuation to be bigger rather than smaller, wouldn't you? Yeah. If it's imperative that you lose as little signal as possible, you might rather be a bit over than a bit under. So it's worthwhile, if it's a long way away, just going and trying the other one and seeing which way it push it. Do you understand what I mean by that? So you could try either option, above and below what the ideal is. So we're going to use a 680 here anyway. And then we calculate again, and it tells me, one, what the decibels value is going to be with those preferred values. So instead of 6.02, it's going to be slightly lower at 5.67 decibels. The input impedance, instead of being 500 ohms, is 482, so it isn't going to quite match that side. Okay. Output impedance is going to be the same, isn't it? Because the same values. Yeah. So they're effectively the same. So you can see that by using preferred values, you've made some changes to from what you wanted to what you get. There's a difference. Now, when you actually come to build it, that 680 ohm resistor could be more than that or less than that by 5%. Yeah? So again, that's going to take it, it might take it back closer to what you designed, or it might take it a little bit further away. They're all things for you to analyse from your practical results and talk about whether that, how close it is. Is that design software, that help, a valuable help to you to get as close a design as you possibly can to what you want in the first place? Is it a valid assistance to software? Yeah. All right. So that's what I'm going to be. You can have a go and check. For a practice, you can check the Pi design and see if we get the 1500 and the 375 and see what preferred values to do with that. And you might find, because we can actually pick, because on this preferred value thing, because we got 150 here, we can effectively pick exactly as a preferred value 1500 ohms. That's got a, well, in this place you'd get one with a 5% tolerance. Yeah. Yeah, it is. Exactly. But because in this case, because you're dead on a preferred value, you might be better off going with the Pi design, because it gives you a closer, you get closer to your design values. I mean, what was the other one? 375?
375 and 1500.
So you could pick a 390 for that. That might be closer than the T design. But 330. So the 390 is closer. But that doesn't necessarily mean that's the best in any particular design. You're going to be fixed to either a Pi or a T anyway by me. But that doesn't stop you saying, well, if I used a Pi design, that might be closer. Okay, if you can fit it in the words I give you in the assignment. Alright? But that's what you're going to be doing for the attenuator, designing that. So you can have a go at the Pi design. Right. This bit is your attenuator. In total, it equals 500 ohms. Yep. Here are your attenuator input terminals. Yep. Connected to your source with an internal impedance of 500 ohms. Okay. Designed to give you 0 to 20 volts at these terminals. As soon as current flows through that resistor, you're going to get a volt drop across it. You're going to lose some of that voltage. So effectively, we could redraw this circuit. We could simplify it into this. 40 volts, 500 ohms. There's our source. All of that together measures 500 ohms. Now remember I said when you measure the input terminals, Lewis, with that disconnected, that's got to be what it measures with the load connected. Yeah, that's the load, and R4 is being the internal impedance of the source. Yep, this always causes trouble, this bit. Yeah. If you can get it, you'll be doing well. All right. So think about that. 1000 ohms, 40 volts. What's the current? Quickly. Calculator. 1000 ohms in total, 40 volts. What's the current? 40 milliamps. So we got 40 milliamps there. Now calculate the volt drop across there. 40 milliamps times 500 ohms. 20 volts. So the 40 volt source, by the time that's lost some of it, that's going to lose half its voltage to its own internal impedance. Yep. Do you get that now, Carl?
I get it, but if that's going from an instrument on the field, such as the pressure transducer, then it's supposed to give off 20 volts.
Yeah, but if what that would give, that's what it'll give off when that's loaded. That's why it specifies what the impedance of it is, because if you measure the voltage of it when it's open circuit, you'll get a much higher voltage than you will when you put the load on it. Yeah, yeah. So if that was a sensor and I connected it all up, open circuit, at top pressure, I'd get 40 volts out of it. Yeah, because the voltmeter is not going to draw a significant current, and therefore I'd measure 40 volts. But when I connected my 500 ohm to it, then I'd only measure 20 volts. Yes, yeah, alright. It's a little bit difficult concept to get, but once you've got there, so in multisim, what we need to do, and I'll save this and we'll pick it up next week now because we're just about finished, but we're not going to need to put a voltmeter here to measure the input voltage and a voltmeter across there to measure the output voltage. Not here. We know that's 40 volts, but that's irrelevant. When we want to see what voltage we're getting out at the maximum 20 volts, we'll have that set to 40, but we should measure 20 here. It won't be quite that because of that mismatch we've got with the preferred values. But we'll finish that off next week. Alright? Yeah?